Let's look at the principle and structure of the Thermatron RF8 hyperthermia system. Professor Saito of the University of Tokyo will explain.
This apparatus is called a thermatron. It uses a rather low-frequency electromagnetic field to heat tumors. The body of the heating system is behind the bed. This is where the energy is emitted. The energy goes into the electrodes and heats the patient's body, which is between them. As I will explain later, the cooling system is very important. Cooling water circulates around the electrodes to cool the surface of the body.
How does the Thermatron RF8 actually heat? Here, infrared thermography is being carried out on an agar phantom, which shows the temperature distribution pattern. This is the phantom used in the experiment. Its electrical characteristics are the same as those of muscle. It measures 21 centimeters thick, 32 centimeters wide, and 29 centimeters long, and the section is oval. Electrodes of 10 centimeters and 21 centimeters in diameter are used for surface heating. The blue color before heating represents about 36 degrees centigrade. The color begins to change following elevation of the temperature. Green represents 39 degrees, yellow 41 degrees, and red 43 degrees centigrade. Electrodes of 14 centimeters and 21 centimeters in diameter can selectively heat subsurface or relatively shallow areas. An area 5 to 6 centimeters under the surface is substantially heated. For concentrated heating of a deep area 12 to 13 centimeters under the surface, 2 electrodes 21 centimeters in diameter are used. Here we can see well how the central area is heated. The central area is heated to 43 degrees centigrade approximately 3 minutes after heating is begun. It is very important to cool the surface of the body during heating. Just under the electrode is a layer of subcutaneous fat, under which is a layer of muscle. As fat has high electrical resistance, it generates more heat when an electric current flows through it. Moreover, the lines of electric force are fairly concentrated near the electrode, where more heat is generated. When air is in a body cavity, as shown in the illustration, the electric current is pushed aside to produce an area where the lines of electric force are concentrated, that is, where more heat is generated. This effect should also be noted. Recently, a device was developed to lower the high temperatures generated around an electrode, or in the area in contact with an electrode pad. This device is called an overlay bolus. It is a flexible polyurethane bag containing salt water with a temperature that can vary from 3 to 40 degrees centigrade and which circulates freely. The overlay bolus evenly distributes the effects of the lines of electric force, and the high temperature produced in a localized area on the surface above the heated area is greatly lowered. Furthermore, by the use of pre-cooling, it has been found that excessive heating can easily be prevented, even of a fat layer about 25 millimeters thick. Thus, excessive heating of the subcutaneous fat layer, burns at the edge of the electrode, and a hot feeling and dull pain which are the disadvantages of an apparatus of the capacitance type, are virtually eliminated. It is very important to monitor the temperature of a tumorous area as well as the surrounding normal tissue during heating. At present, an invasive method is employed in which a needle puncture is made in order to insert a catheter for accommodating a very thin, flexible temperature sensor. This is the temperature monitoring system of the thermotron. It can measure the temperature at 5 positions simultaneously. This slim part is inserted into the tumor to measure its temperature. The tumor does not have a uniform temperature distribution. The temperature is high in the central area and relatively low in the peripheral zone. Therefore, it is necessary to use multiple point linear array thermosensors or measure at multiple monitoring sites. Let's look at the actual placement of a temperature measurement device with the assistance of members of the Department of Radiology of Kyoto University. At first, the skin surface above the lesion is sterilized and local anesthesia applied. Next, a catheter is inserted into the target tissue. In this case, 2 catheters are introduced into the target tissue, transversely and vertically. A thermocouple is inserted into the lesion via the catheter sheath, following removal of the catheter needle. It may be necessary to cover the skin punctures to avoid infection. Ten minutes have passed. The thermometers indicate 40.6 degrees and 41.2 degrees centigrade. During heating, the temperature sensor in the catheter track is drawn out at 1 centimeter intervals to scan the temperature distribution. The temperatures from the center to the periphery are recorded. The temperature profile is mapped before, during, and just before the end of therapy. Now, a multi-point sensor is used which can measure the temperature at 4 linear points simultaneously. In this case, in which a cancer has metastasized to the liver from the lung, the catheter track for temperature sensor insertion was directly placed into the abdomen by laparotomy.
We selected some representative cases in which good results were obtained by hyperthermia using the thermotron RF8. This is a case with a malignant rectal melanoma in a 69-year-old female. Metastasis is found in the lymph nodes bilaterally, and the right lesion is larger than the one on the left. In this case, with bilateral metastases, one lesion was treated with radiation and heating, while the other was treated with radiation alone. The results were then compared. This is a CT scan obtained after radiotherapy with a total of 4,000 rad and 10 courses of hyperthermia on the right lymph node. The metastasis has virtually disappeared, while the left lesion, treated with radiation alone, still remains.